Okay, so good evening, everyone. Let's start our tutorial session for today. So this is the tutorial session on the NPTEL course on mechanism and robot kinematics. It's Krishna Avatar here. So today we'll be reviewing some of the aspects of velocity and acceleration analysis from the module 3, module 7 of this course. And then also we'll be continuing our lecture special topics on Euler angles and Quaternions today. So let me begin with the velocity analysis with some of the aspects that we have been talking about. Okay. Just a moment. Okay, so we'll start with velocity analysis. So as you recall, velocity analysis indicates given actuator slash joint rates, we determine the end effector rates, right? So that is overall the mechanism that we are talking, overall the mechanics, so to speak, right, of this particular velocity analysis. And this could be posed as a both forward and backward problem or inverse problem. So in the forward problem, what happens is that given certain actuator or joint rates, we have to determine the end effector rates. And for the inverse problem, it is the vice versa, provided or for a given or for the desired end effector rates, what would be our actuator or joint rates. So that's what we are talking about, right? So today let's revise what was talked about in this module 7, and it was on let's begin with, so this as I'll just mention it here, that we have forward problem, right? Forward problem and inverse problem, right? These are the two aspects of velocity analysis, right? And today will be let's begin with what we call as the planar 2D robot. And 2R robot, because here R in implies that this robot has two revolute joints, right? So how we deal with this, let me just make a schematic of how things are here. So say these are the X and Y coordinates. We have one joint link, a ground link here, and this is the first link, and this is the second link. And there is another the first R joint and the second R joint. And this is our end effector. And it's inclined at certain angle with respect to the horizontal x-axis, and it's angle phi. This is angle theta 1. And this is inclined. The second link of length L2 is inclined with respect to the link L1 by an angle theta 2. Right? And the instantaneous rates are, so to speak, theta 1 dot and theta 2 dot for the both inclinations. So here the goal is that given the configuration theta 1, theta 2, we are to determine the relation between theta 1 dot, theta 2 dot, and xe dot, ye dot. Right? Now, when xe and y are these are the coordinates of the end effector, right? And the rates would be inclined at some, the velocity of this end effector would be some direction, which of course has to comply with the constraints of imposed by the very very geometry of this robot. So yeah, so that is our velocity of the end effector. And now let me just write down the coordinates of the end effector, right? So x coordinate would be L1 cosine theta 1 plus L2, and here just to add here that let's draw a line, dotted line parallel to the horizontal axis, and by the rule of transversal, this angle is equal to this angle, right? So it means this would also be 1 theta 1. So which means that now we have xc L1 and cosine theta 1 plus theta 2. Likewise, y is equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. So essentially, this is what our coordinates of the of both the x2 and y are, right? And also uh, now what we do is, and we just differentiate, or I'll just put it somewhere so that we have enough space in the slide itself. Okay. So these are the x and y coordinates. Now what we do is let's differentiate. So differentiate xe and ye with respect to time to get, so xe dot is equal to L1 and then cosine theta 1. When we take a derivative with respect to time, we'll have to use the chain rule, right? So this will be first differentiate with respect to theta 1, so it gives minus sine theta 1, then theta 1 with respect to t, which means that theta 1 dot. Likewise, for the second term we have L2, then minus first with respect to theta 1 plus theta 2, which is minus sine theta 1 plus theta 2, and now with respect to time, so it means that theta 1 dot plus theta 2, right? And what we can do is we can just rearrange them in this form, this to have, say, uh, minus L1 something like this, minus L1 sine theta 1 plus then L2 sine theta 1 plus theta 2 whole multiplied with theta dot. Likewise, for the second term, we have minus L2 sine theta 1 plus theta 2 into theta 2 dot, right? Likewise, let's have repeat this process for the y coordinate. Then this gives us that we start with we again invoke the chain rule. So we have L1 cosine theta 1 dot plus L2 cosine theta 1 plus theta 2, and likewise theta 1 dot plus theta 2. And this gives us just clubbing terms with theta 1 dot and theta 2. So we have L1, L2 cosine theta 1 plus theta 2, theta 1 dot plus L2 cosine theta 1 plus theta 2, and then theta 2 dot. Right. Now what we can do is uh, let's form the let's form a matrix equation out of both these equations. So this gives us xe dot ye dot, and this will be equal to, so we have minus L1 sine theta 1, and then also minus L2 sine theta 1 plus theta 2, and here we had minus L2 sine theta 1 plus theta 2, and for xe dot we had L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2, and here we have L2 cosine theta 1 plus, cosine theta 1 plus theta, and this is theta 1 dot theta 2 dot, right? And this matrix we call as J. It is some Jacobian. Mind you, this Jacobian is a very generic name. It only helps, it is some sort of a function which helps us to map from one coordinates to the other. And you will often find it also being used in, say, multivariate calculus when we are transforming from one set of coordinates to the other, right? So this is a very generic thing. It's not very specific to this problem. It's a generic mathematical tool to help us convert, transform from one set of representation of something to another form of representation, right? So here this vector is what we call as the actuator rates, or of course we can also call it end rates. So let's call it actuator rates. And this is our end effector rates, and this is very clear from our schematic itself, isn't it? Right. Now, yeah, we can also write this as xe dot vector is equal to j theta dot vector. Then this, as you recall, xe represents this vector here, and theta dot. Fine. Say we want to take an inverse. Say we want to determine the inverse. And as it may click, so why would we want to find the inverse, right? So the very purpose of inverse again follows from the earlier part of discussion, where we had talked about inverse problems. So likewise here also. So we would like to find the inverse of this equation only if we want to know theta dot vector, provided that we already are aware of xe dot vector, or for any desired xe vector. So this is of course for the inverse problem, and this is for the forward problem, right? Now what we do is, let's try to determine the expression for J inverse. And we would also, on the way, we would also want to talk about uh, the singularity and other such concepts, right? So given that, uh, say we have J matrix is given as J11, J12, J21, J22. As we recall from we can substitute the corresponding coefficients of this matrix just by comparing with what we had on the previous slide. So schematically or say symbolically, we have J inverse is equal to, first you find the determinant of J. So what is the determinant of J? So determinant of J is J11, J22 multiplied with J22 minus J21 and J12. Right, so this is what the determinant is, and J inverse is given by 1 by a determinant of J, right? Determinant of J, and then the adjoint of J. Adjoint means we have J22, and for this is J12 adjoint this the cofactor of J12 is will be minus, so it will be minus J12 itself, and taking the inverse, right? Sorry, the transpose. So here it will also be minus J21, and this is of course J1. Now let's uh, put the substitute the expressions for all these components. So J11, so let's start with determinant first. So determinant of J is equal to, of course we had minus L1 sine theta 1 plus L1, sorry, L2 sine theta 1 plus theta 2 multiplied by what we had is L2 cosine theta. So L2 cosine theta 1 plus theta 2, and then minus of, and then we have minus of L1 cosine theta 1 plus L2 cosine theta 1 plus 2 into minus again. So it effectively be plus. We have plus L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2 into L1 L2 sine theta 1 plus theta 2. So this is what it is. Let's try to expand it, isn't it? So the first term is minus L1 L2 and cosine or maybe sine theta 1 cosine theta 1 plus theta 2 plus L2 squared sine theta 1 plus theta 2, then of course cosine theta 1 plus theta 2. Likewise, and here also it was supposed to be minus. Now we have plus L1 L2 sine theta 1 plus theta 2 into cosine theta 1 plus L2 squared sine theta 1 plus theta 2 cosine theta 1 plus theta 2. What we see is here with these two terms, the second and the fourth term are of opposite signs, right? So we can just cancel them out. And now what we do is we can take L1 L2 as common, and then say we have sine theta 1 plus theta 2 cosine theta 1 minus cosine theta 1 plus theta 2 sine theta 1, and this makes us L1 L2 sine theta 1 plus theta 2 minus theta 1, right? So we have L1 L2 sine theta 2, right? So this is what our J essentially is. I mean, sorry, determinant of J essentially is. So now what we have to do is, so J inverse is equal to 1 by L1 L2 sine theta 2, And we have J22, which is L2 cosine theta 1 plus theta 2. And then here minus, we had J21, right? This is L1. So it was J12 itself. So it is going to be, it was J12. So it is going to be L1, or maybe, yeah, L2 sine theta 1 plus theta 2. And in this case, we had minus, so it's minus of L1, okay, minus L1 cosine theta 1, and of course minus L2 cosine theta 1 plus theta 2, right? And here we have is L1 sine theta, it will be minus again, minus sine theta 1 minus L2 sine theta 1 plus theta 2, right? Now let's take a look at this inverse, J inverse here. Say if determinant of J is equal to 0, this implies that then we end up at some singularity, at a singularity. So as you recall, as we had talked about it last time, so singularity here implies that no matter, so for a given, I mean physically what would mean, right? Physically it would mean that for a given, if J inverse, determinant of J is say 0, then J inverse is infinite. Then what happens physically, it would imply that given some, or for some desired end effector, we would require, because of this the scaling with because of J inverse, we would require infinite joint rates, which is never possible, isn't it? So that's the result. This is the reason that the singularity here implies that there are these are the states which we would not be able to attain it, which means that there will be certain end effector rates which we won't be able to attain at certain configurations, which is determined with, which are given by theta 1 theta 2 combination, isn't it? So that is what singularity essentially is. Now what are those points? Now say we know that the determinant of J was given by L1 L2 and sine theta 1 sine theta 2. So L1 L2 sine theta 2 is equal to 0, isn't it? So this implies that of course L1 L2 is not are not going to be 0. So this means that theta is either 0 or pi, or in a general form theta 2 is equal to n pi, and for our restrictive case we would allow it to have, say, theta is equal to 0 and pi. So these are the two configurations, because these are the only two configurations which are unique. The rest are just say it will just they are just repetitions of these two configurations. So which implies that for the 2-hour robot here, let's allow the since the determinant of J does not anyway depend on theta 1, so theta 1 say can take any value, but for theta 2, if it is located in this configuration here, and in this case say the angle made by the link 2 with respect to link 1 is this here, theta 2 is 0 because they are aligned, right? So this is where we have and then these are of course the x, y coordinates which denote the poisons, the poison of the position of the end effector. Now theta 2 is equal to 0 is this one such configuration, and at this configuration it is going to be singular. The determinant or J matrix is going to be singular, and there the other such configuration is when we have, say, theta of 1 can take any value, of course, and when this J, the second link here, say we start from here and rotate it completely by pi. So this is our theta 2. Theta 2 is equal to pi. And at this configuration is where we have a singularity in the of the system. Fine. Now we would always want to avoid situation. So we would want theta 2 to remain far away from such configurations so as to be able to actuate the system, actuate the robot, otherwise it will not be possible. So the farthest from this position, of course, implies that thetas should be, say, closer. In general, just speaking. So like if it is, say, theta 2 is somewhere around 90 degrees, those are the locations where it's farthest, where the second link is farthest from attaining that singularity, isn't it? With this brief discussion, now let's also move on to acceleration analysis just for this system. I'm sure you are already aware of the other, since the lecture notes are quite exhaustive and self-explanatory. So the second part is acceleration analysis. That's where we are going to talk about. So in the acceleration analysis, now the question comes is, why do we need it? Now recall, velocity analysis helps us to determine the direction of the direction and the rate, right? Instantaneous rate and instantaneous, so to speak, speed, right, of the end effector. So this, of course, implies that gives us the path of the end effector. Right? So this is the reason why we say this is the advantage, or so to speak, the goal of velocity analysis. Right? Now we also need to determine the acceleration, right? Acceleration implies that we are able to estimate the force input to the actuators. That is the reason we need to do acceleration analysis. That's one of the basic aim of doing an acceleration analysis, that it helps us to the goal, of course, becomes linking or trying to determine the relations between the accelerations of the end effector as well as the actuator, the actuators or the joint joint rates. But however, we require it to determine our equations of motion and also be able to provide to specify how much load or force is required to carry out or to reach our desired end effector position or orientation, isn't it? So that's the very purpose of doing this. Right. Now let's talk about so this is the entire this part comes under what we call as the path planning. So in path planning, just for this schematic, what we have is, so this were of course our, let me, so we have theta 1, theta 2, theta 1, and then this is theta 2, and of course theta 1 dot, theta 2 dot, and we would try to estimate uh, what is the rate at every point from, say, we start at t is equal to 0 here and then land up here at t is equal to tf, which is final time. So at throughout this process, what we want to know is what are the values of xt and yt as a function of time, because that's what helps us to determine the path, isn't it? And then doing velocity analysis and accelerances helps us to determine the velocity and acceleration profile along the path, right? Coming back here, so, and then let me again go back to this expression here, right? This expression. I hope I'm able to copy it. Yeah. And then uh, so this was our xe dot. Now what we do is differentiate again with respect to time. So the left hand side becomes xe double dot, while the right hand side becomes, now it becomes a complex. Of course, there's a complex exercise in algebraic manipulations, right? So we start with the chain rule. So in the first case we have, let's have L1 cosine theta 1 dot plus L2. So again here as well, cosine theta 1 plus theta 2, and then theta 1 dot, theta 2 dot, and of course theta 1 dot. Now then we have L1 sine theta 1 plus L2 sine theta 1 plus theta 2, theta 1 double dot, and then we have L2 cosine theta 1 plus theta 2, theta 1 dot plus theta 2 dot into theta 2 dot minus L2 sine theta 1 plus theta 2 double dot, right? Now what we have here is minus, sorry, so this keeps on happening every once in a while. I hope that, okay, fine. This was, we had L1, L2 sine, rather, yeah, sine theta 1 plus theta 2 into theta 2 double dot. Now let's expand them. So we have minus L1 cosine theta 1 dot double squared plus, or again minus, sorry, we have L2 cosine theta 1 plus theta 2. And in this case, we have theta 1 dot squared plus theta 1 dot theta 2 dot. And in this case, what we have is L1 sin theta 1 double dot plus L2 and here we have is minus L2 cosine theta 1 plus theta 2. We have theta 1 dot theta 2 dot plus theta 2 dot whole squared minus L2 sin theta 1 plus theta 2. Right, now let's just collect terms with say theta 1 dot square terms. And before that, let's see if there we had here, it should have been minus. Do any of these terms cancel out? Okay. I don't think we're able to cancel out, so let's have it as minus L1 cosine theta 1, then we have minus L2 cosine theta 1 plus theta 2. This will be theta 1 dot squared. Then the rest is L1 minus L2 okay. So fine. Okay, so minus L2 cosine we have theta 1 plus theta 2. This is what again it comes from here as well as here, so it's like 2 times, right? So minus 2 times of L1 L2 sorry 2 times of minus L2 cos theta, then you have theta 1 dot theta 2 dot. Then what we have is this is going to minus here as well. Right? So what we have is minus L2 cosine theta 1 plus theta 2 dot squared. Then the rest we have L1 sin theta 1 double dot the minus of course plus L2 sin theta 1 plus theta 2 theta 1 double dot, like the last term is L2 sin theta 1 theta 2. So this is the just for expression for xc, right? So here I just want to mention certain aspects. That the first aspect that you see here is even if theta 1, even if say a theta 2 double dot and theta 1 double dot is 0, it still implies that xc uh, double dot or the acceleration of xc is not 0, right? Just because of the presence of the squared velocity terms. So this implies that what I want to say is that we have xc double dot some function of theta 1, theta 2, 1 dot dot. That's not the case. And then theta 1 dot, right? And some function of theta 1, theta 2 dot squared, right? And again some function of h1, h2, theta 2, theta 1 dot, theta 2 dot. Then the other functions are just linear relationships. Something into theta 1 dot double dot plus something into theta 2. So what we clearly see is even if theta 1 double dot is equal to theta 2 double dot is 0, still we can have xc dot double dot not equal to 0, right? Just because of presence of this velocity terms was squared, and then also the cross product or the product between two different velocities, or maybe so to speak the coupling between these two velocities. Now this is because of centripetal force, right? And all that, because of that we have all this squared velocity terms, something of these forms, right? So this is what we essentially have. And this was to be discussed in the week for the week 7 of this course. Now let's move again to dealing with the special topic that we have been trying to jointly study, right? Special topics. So today we would be continuing Euler angles. So far we had covered the Euler angle rotations. I mean what are Euler angles, what are the elementary rotations, how do we construct Euler angle rates and all that, isn't it? We have been able to cover all that. What are the say what are the valid rotation sequences? This is all we have been able to cover, right? And we are also talked about the relation between the Euler angle rates and the Euler angle velocity, so the angular velocity, so to speak. And we also talked about the conjugate Euler angle rates matrix. So this all we have been covering. We have been able to cover so far. Now, and we talked at length about Euler angle sequence 313. Implies that we are first rotating about, say, the third body axis, or maybe the third axis, whatever convenes other, if we are whether we are in, say, the world coordinate system or the body fixed coordinate system, and then rotating about the second sequence, second step in the sequence would be to rotate about the first axis of that transformed system or transformed coordinate system, and then the third step would be rotation about the third axis of that say transformed coordinate system, right? So that is what we have talked about. And then we were able to link it to rotation, how we are able to construct a rotation matrix from the Euler angles, and also to extract the Euler angles from those rotation matrix. So today what we would do is let's talk a little bit about the Euler angle rates. Euler angles. Provided given some Euler angles, what are the Euler angle rates matrices? Right? Now, as we recall, the way we constructed Euler angles was that Euler angle rate matrices, if we have say three parameters phi, theta, and psi, this was defined as Rk psi transpose Rj theta transpose and then Ei comma Rk psi transpose. Right? So these are so here and for our sequence what we would have is we have E313. So it means that I is equal to 3 and j is equal to 1 and k is equal to 3. So this we have as R3 with a rotation psi and R1 theta transpose and then E and I is 3. Right? So R3, EI3. And here we have RK is 3 psi transpose EI, J is 1 and then we have so this is what we are talking about. Now how do we construct? Let me just take up this expression, copy it. And mind you that this E1, E2, E3 are the standard Cartesian coordinates. Now what we talk about here is we would first like to have the expressions for R3 as a function of psi. Let's just determine it. We have cos alpha, sin alpha, 0, 0, minus sin alpha, cos alpha, 0, 0, 1. And of course, R1 theta would be, so it's about yx, about the, say, the one axis, right? So we have the first column and the first row would be 1 followed by zeros. Then what we have is cosine theta, sin theta, minus sin theta, and then cosine theta. Now R3 transpose psi transpose is just cos alpha, sin alpha, or sin psi, right? It was psi here, psi, psi, then cos psi minus sin psi, 0, 0, 1, of course, and then sin psi, cos psi, and likewise R1 theta transpose is equal to 1, 0, 0. And say when we multiply, right? So R3 psi transpose into R1 theta transpose, and this is equal to first column, sorry, first row, first column. It's cosine psi first column, then second row. What we have is minus. I'll use that shorthand so that it's not very clumsy here. So minus c psi, then we have minus s psi c theta, and then we have s theta s psi, right? Then we have uh, s psi 0 0, and then c psi c theta, and here we have minus s theta uh, s theta c psi. Over here we have 0 s theta c theta. This when multiplied by e3, which means 0 0 1, what we have is last column, which is s theta s psi minus s theta c psi. This when multiplied with e3. Likewise, r3 multiplied by e1 with the first column. So we have c psi s psi 0. So effectively our e1 e313, which is a function of phi theta psi, this is given by s theta s psi minus s theta c psi c theta. What we have here is c psi s psi 0. And the last one is 0. This is what we expect from doing all these operations. Yeah. So this is how we relate omega on Euler angles, sorry, the angular velocity with respect to 313 to u vector dot, where u vector is nothing but phi dot, theta dot, and psi dot. So this is the Euler angle rates, and this is angular velocities. Right? Now the inverse of E313 or phi, this would help us to get why we need it. This is just so that we are able to determine u dot for some given angular velocity omega. Now when we do it, when we upon finding out the inverse of this E313 of psi inverse, this gives us The determinant is, of course, so let's just find the determinant. It would be, I think, a very straightforward exercise. So determinant of E313. So say, let's find the row or column in which we have the maximum number of zeros, so that we would like to take the expansion in terms of the minors or the minors along those along the elements of that row or column, right? In this case, what we see is that the third column 001, we have the maximum number of zeros, so it reduces our efforts quite a bit, right? So when we expand around it, then the third element here is 1, so it will like 1 and the minor of 1, or the cofactor of 1, I would say. So the cofactor of 1 would be given by s theta, s psi, and so let's see again, s theta, s square psi, then minus into minus plus, so we have plus s theta, s square c square phi, and this gives us, you can have s theta outside and then do the rest. So it is sine s square psi plus c square psi, which is 1. So we have s theta. So the determinant is just s theta. So we have something by 1 by s theta and all the expansions which we don't require it right away, but of course let me just, even then let me just put out the values. So s theta c psi minus s psi c theta minus c psi 0 0 s theta s psi and then c. So what we see here is, again, what we had learned in our module 7 revision, that singularity arises when s theta is equal to 0. This implies that theta equal to 0 comma pi, or in general n pi, right? So in this case, what happens is that the at this there will be that the change in spin and precession, they will constitute the same motion. It is as if you are unable to get a proper values. So they become like in this case, the phi and psi would become degenerate. So that is the problem here, right? So here phi and psi becomes degenerate, which means that they are the one and the same motion. And that is the reason we would always want to avoid such scenarios where, say, theta happens to be or we would like to avoid scenarios where theta is close to n pi, isn't it? Now let's open a new frontier here, as we had planned for the day today. In the note that I had asked all of you to download, and which I am also following, there are few more angle sequences such as 1, 2, 3, but we are not going to be talking right now, since they would be just repetition of what we had learned. Our goal now is to introduce ourselves to quaternions. Now, a brief history about quaternions. So it was devised W.R. Hamilton. He is a great figure in the field of classical mechanics. And of course, you must have heard of Hamiltonian principle, or Hamilton's principle. So it was devised by him. In general, Quaternion is an extension of what? Complex numbers. So complex numbers in 2D, because as we recall, complex numbers, we used to write it as z is equal to x plus, complex into which is z is equal to x plus iy, to 4D, such that we have is equal to q naught plus q1 plus q2j plus q3k. And mind you, ijk are extension or iota in 3 different space are equivalent to I, the classical iota, in 3 different, in 3 spaces, or sorry, 3 coordinate directions. That is what the idea came from about quaternions. And they have to satisfy a constraint. There is a constraint. So although you would feel that, okay, there are 4 numbers, however, they are bound by a constraint such that you have q naught squared plus q1 squared plus q2 squared plus q3 squared is equal to 1. So this is the constraint. So it's effectively, it reduces us to determining just the 3 numbers. And we are able to sign up to sign, we are able to obtain the value for the fourth the component of the quaternion. Now generally how do we define for a general quaternion, right? So a quaternion q vector is an element of H. So H is that Hamiltonian space, if you can call it like that. I would just call it is represent or can be represented as a vector is equal to q naught, q1, q3 transpose, and in short form we have q naught and q vector 1:3. Now we can apply all those additional definitions, such as the adjoint is equivalent to conjugate for this complex analysis. We have q vector bar is equal to, so conjugate of in this form, in the complex form, right? It will be the adjoint will be q naught minus q1i minus q2j minus q3k. So because of which it's like the last 3 coefficients, the sign gets, so to speak, altered, or maybe. So we have q vector 1:3. And the norm of this quaternion q vector is equal to q naught squared plus q1 squared plus q2 squared plus q3 squared. And of course, inverse is equal to the adjoint divided by the norm of Q. Okay? So this is what we had, isn't it? Coming back, so we won't go very far since like I'll just be spending some few minutes and then we will talk in length in the next class. Let's talk about a very important topic in quaternion, which is quaternion multiplication. Right. So we must be reminded of the fact that quaternion multiplication is not commutative. It is not commutative. Means that for any two quaternions P and Q, Q dot P is not equal to P dot Q. So they're not commutative. How do we define, now the question remains, how do we define quaternion multiplication? So quaternion multiplication between the quaternions P and Q is, so we have say Q dot P, this is equal to say some operator Qm. Of course, if we multiply two quaternions, then we would get another quaternion, right? The third quaternion. So say Qm, say is the end product, and this would take arguments as Q and P. This is defined as in matrix form. We can write this as, or in a vector form, Q naught P naught minus Q vector 1 is to 3 transpose P vector 1 is to 3. Right? So it's a scalar. Now here we have Q naught P vector 1 is to 3 plus P naught Q vector 1 is to 3 minus Q vector 1 is to 3 cross P vector 1 is to 3. So this is like cross product. So the second row sort of this vector is essentially another vector of size 3 cross 1, right? And then we can construct write this down in terms of a matrix vector product. So we can have say P naught and P vector 1 is to 3. Thus, this what we have here is Q naught P naught and minus Q vector transpose 1 is to 3. And in the first one, what we have is, let me slightly extend it. So here, what multiplies with P naught is Q 1 is to 3, and then we have Q naught, and it has to multiply with P 1 is to 3, and this would be something equivalent to I 3, and I 3, as you recall, is the as you may know, it's the identity matrix of third order, right? And then in here minus, of course we have cross product of q1:3 with respect to p1, so it's, and q13 is 1:3 is a vector, and it would have an equivalent skew symmetric matrix, right, that we call as the some sort of the matrix, the skew symmetric matrix, which was that axial, whose axial vector is q1:3. You have q is a matrix, and then q vector 1:3. So this is one way of, and then here C is that cross product matrix. The C is of any vector x is given as 0 minus x3, x2 minus x1, and then 0. This one was x1. So this will be x1, this will be minus x2, and this will be x3. Right? So essentially what we have here is that so what we had here was and so q dot p, just copy all this as very relevant things. And this we can also write it in another form with the q as an argument. So q naught, then we have q1:3. So q naught argument would give us, this would be p naught, and this will be p transpose 1:3, and require, so here what we had is q naught will be p is 1:3, so it will be p 1:3, and the last one what we would have is p naught so now this term is equivalent to minus of p1:3 cross 1:3, so it becomes plus of p1:3 cross qs. So it's like plus. So what we have here is p naught y3 plus c of p is to 1:3, p vector 1:3. So in short, we can write this as q vector dot p vector is equal to matrix product q vector is p, and then we could write it as q vector into p vector, right? And this is the same as q of the conjugate of p into q vector. And this happens to be our q And this we can call it as Q transpose of P vector. So Q conjugate of P vector. And this we call as the Quaternion matrix function. And it maps from Q is to H, which was Hamiltonian space, to R 4 cross 4. Right. This does the same. It also maps Q H is 2 4 cross 4. Now there are certain so this is the conjugate, right? Conjugate Quaternion matrix function. And we have a relation that Q of Q conjugate, Q of Q conjugate is the same as Q conjugate, Q of Q transpose. Likewise, the conjugate of Q transpose of Q, the adjoint of Q, small q, is the conjugate of capital Q transpose. I think for today's session, let's keep it at that. In the next session, we would be still continuing. We'll continue Quaternions and talk about and discuss about rotation vectors, and also be reviewing some of the aspects of weak 8. That's of course. And I believe the next session will be the last one. So yeah, we'll by next we would be able to cover the entire node that we were to talk about, right? Okay, so I'll just close the meeting.